Good morning and welcome to the FAÇADE webinar series, episode 14. My name is Laetitia Marot. I am a Marie Skłodowska-Curie Fellow at the InnoRenew Center of Excellence, and today we will talk about bioactive-releasing polymers and how to use CO2 as a renewable resource for innovative technologies in polymer science. I'm very pleased to welcome our speaker, Dr. Mathilde Champeau, who is an assistant professor in materials engineering and coordinator of the Laboratory of Supercritical CO2 Technology and Polymer Materials at the Federal University of ABC in Brazil. Dr. Mathilde Champeau is a material scientist. Her research activities include CO2 valorization by supercritical technology to obtain functional polymers such as bioactive release systems, and the development of new precursor gels for 3D printing and optimization of printing parameters. The presentation is recorded today, and as usual, you can send your questions in the chat. I will read them at the end of the presentation to Dr. Champeau. So now let's talk about bioactive releasing polymers. Dr. Champeau, you can start.
Thank you very much, Laetitia, for this nice introduction. Good morning, everyone. It is really early in the morning here in Brazil. I am Mathilde Champeau. I'm assistant professor at the Federal University of ABC in Santo André in Brazil. And so today we will talk about bioactive releasing polymers and how we can use a supercritical approach for CO2 valorization. So first, a few words about my university. It is a young university, but we have 24 undergraduate courses, some master and PhD programs. Just to locate our university, we are very nearby São Paulo city in Brazil. And even if it is a young university, it is quite well ranked. It is number 3 in Brazil, according to the Time Higher Education Young University ranking, and the number 1 in Brazil for internationalization. And we are very open for collaboration, particularly with international laboratories. So the summary of this talk: first, I will introduce the motivation of this research. Then I will present gradually the different steps of this research, coming from more simple systems to more complex systems. So first of all, we should come back to the problem of CO2, which is a very well-known greenhouse gas. It is the most important one and accounts for about 66% of the warming effect on the climate. And roughly half of the CO2 emitted by human activities remained in the atmosphere. And as you can see on this graph from, as you can see on this graph, the amount of CO2 in the atmosphere is rising, and so this problem must be targeted, and it has been highly discussed during the COP26. And so how do we deal with CO2? So we can try to first capture CO2 and store it from flue gas from thermal power plants and industries. And after capture and storage, either we can sequestrate it in deep geological layers. Either we can use it, so it is highly used for enhanced oil recovery. So it is injected in order to recover oil and petroleum. And it has also different uses in material engineering. And one of them is to produce polymers. So this is part of the project. I will introduce it a little bit at the end. So it is a way to use CO2 and decrease the amount of CO2 in the atmosphere, to use it as a reagent to produce polymers. But also CO2 can be used to decrease carbon footprint. And this is what we do in this project also. We use it to replace organic solvents and to decrease wastewater. So this project that I'm presenting today is an international project, and it aims at using CO2 in 3 different steps and for 2 different roles. So the first one, as I said, is to use CO2 to produce polymers. So we are collaborating with a group in Belgium who is specialized in developing polymer and polymer synthesis. So they produce these CO2 sourced polymers. We also worked with a laboratory based at Unicamp. Unicamp is a huge university in Brazil that is located at 100 kilometers from here. And we are working with them, with this group, with a group specialized in using CO2 as a solvent to extract natural products from natural matrices. So, for example, leaves, seeds, and so on. And this natural extract, we are impregnating them into polymers. So it is what we are doing in my laboratory in order to create polymers that are able to release this natural product in these bioactive molecules. And in order to better understand the thermodynamic of these systems, and particularly the solubility of this natural product in CO2, we are working in a collaboration with the University of Bordeaux with Dr. Thierry Tassin. And just to introduce my laboratory, we are the Laboratório de Tecnologia de CO2 supercrítico e materiais poliméricos. My colleague, Dr. Ligia Passos Maia, and I are working on different strategies to use CO2. And so in this project, we are working together on this part of impregnation. So to talk quickly about the context. So many polymeric products have a specific roles, mechanical role, optical, protective, to control humidity. And it can be interesting to add a specific bioactivity to these products, introducing an active molecule into these polymers. And this leads to developing a polymer able to release this active molecule in the surroundings. So the applications are various. It can be to develop drug-releasing implants in their neighborhood, to develop active food packaging and food-grade materials, or cosmetics. And to load this active molecule into these polymers, generally we use organic solvents, but it presents some drawbacks. This mechanism has a slow diffusion of the solvent into the matrix, so it is time consuming, and also the solvent residues must be removed to fit the FDA's requirements, so it is time consuming, energy consuming, and it costs quite a lot. So the alternative in this project is to replace this organic solvent by supercritical CO2. But what is supercritical CO2? Here is the phase diagram of CO2. You can see that the critical point of CO2 is rather low. It corresponds to a temperature of 31 degrees C and a pressure of 74 bar. And in this state, CO2 has properties between those of a gas and those of a liquid. So it has good diffusivity in solid matrices, and also it has a good solvation power for small and apolar molecules. And its properties can be tuned varying the pressure and temperature, which is rather simple to do in the laboratory. Also, CO2 is recognized as a gray solvent. It is non-flammable. We can process at low temperature, which is particularly interesting when we talk about polymers and bioactive molecules, and it has a low cost. So for all that reason, CO2 is used as a solvent in this project. But how does this impregnation process work? So we place our bioactive molecules or extract that has been previously extracted in our high pressure cell and the polymers that we aim at impregnating. And CO2 will first dissolve these molecules, and then CO2 will diffuse into the polymer and will bring with it the molecule that are solubilized. and we wait the equilibrium to be reached. And to remove the solvent, we just have to depressurize the system. So we control the pressure and the temperature during this process, and we also control the depressurization conditions. So this process has been highly studied to impregnate one molecule into one polymer. So 3 factors have been identified to be necessary to achieve high impregnation yield. So first, the polymer must absorb a high amount of CO2 and swell. We must have a good affinity between the molecule and the polymer, and high chain mobility favors impregnation. So particularly working at a temperature higher than the vitreous temperature of the polymer is beneficial for this process. Just to make it clear, so the drug loading or impregnation yield, I will use different terms in this presentation, is determined as the weight of molecule impregnated divided by the weight of raw polymer. So, as I said, the impregnation of one molecule into a polymer is well understood, and some reviews have been published that identify all the influence of the parameter, thermodynamic condition, and so on the impregnation yield. So now, as I said, we are going towards integration of supercritical CO2 extraction and impregnation in this project. It is one of the goals. Supercritical CO2 extraction is a very strong field in Brazil that can be explained by the fact that we have a diversity of vegetal matrices. So we have extracts with various properties, and these extracts are multi-compounds mixtures. And these different molecules that compose this mixture are complementary and synergistic actions. So in fact, they have higher bioactivity compared to synthetic compounds, and also they are safer. And the extract obtained by supercritical CO2 extraction have a better quality than those obtained from traditional extraction process. We conserve better their bioactivity. And as you can see in the right of the slide, there are quite a good number of startups that have been developed using this process to obtain natural extracts. And so the novelty in this project is to integrate these 2 processes, extraction and impregnation. So we aim at targeting this objective in order to valorize agro-industrial residues and also the Brazilian biomass. And we are working with Professor Maria Angela Meirelles from Unicamp, who is one of the most important researchers internationally in this field. So if we look at the literature, we can find recent and increasing interest of the research community for supercritical CO2 impregnation of natural extract to develop new products and more functional products. So some of them, some of this research impregnated some extracts that have repellent action into fabrics. Others impregnated extracts that have antioxidant and antimicrobial properties for food preservation, for example. So as you can see, by impregnated this mango leaf extract in this food packaging film, so the fruit was better conserved than with the raw film. But there is a lack of a systematic methodology, a lack of knowledge about supercritical CO2 impregnation of multi-compound systems, of extract, and so on. And we aim at targeting these facts because we have a higher complexity than working with one molecule in one polymer. In that case, we have multiple physicochemical interactions. And one of our questions is, do we have a change of the composition of the extract once it is impregnated compared to the crude extract? And so should we expect a change of bioactivity also? So our hypothesis is that probably we have specific phenomena that affects the thermodynamic behaviors, and that affects the impregnation of the extract. So we aim at understanding that in order to set some guidance for selecting adequate polymer and extract pairs and operational conditions in the way to conserve better the composition of the extract in the polymer, and so to preserve the desired bioactivity. So that's why in this research, in order to answer this question, we have an incremental degree of complexity in our system. So first, we focused on the impregnation of model systems. So we selected mixtures of two molecules impregnated in one polymer. After we went to the impregnation of a simple extract in one polymer, and now we are going to impregnation of this extract in blends of these polymers obtained from CO2 source polymers. So first, let's talk about the impregnation of these model systems. So this is the master degree of Isabella Coutinho. We've selected two polymers, PLLA with a polyacid lactic and polyethylene, in three different drugs, aspirin, carvon, and cetoprofen, that have been selected for bearing different chemical groups. And we started with the impregnation of polyethylene. So what we've done is we first impregnated each of these drugs separately in polyethylene, and then the combination of two of these drugs, and we compare the results. So first of all, we observed that independently on the conditions that we used, the impregnation yield is very low in polyethylene because we have no specific interaction between CO2 and polyethylene. There is and also no interaction between these molecules and polyethylene, for being a very simple polyolefin. So no specific, if we compare the impregnation yield of this drug separately and the impregnation yield of this drug, this combination of drug, we observe that the combination of drug results in simply the sum of each impregnation yield of each drug. So in that case, we said we don't have specific phenomenon, and we can predict the impregnation of a mixture of this drug using the data obtained from single impregnation. Then we focused on the impregnation of PLLA. So as you can see, PLLA is a polyester. We observed that by increasing the pressure and temperature conditions, since we were above the TG of PLLA, we observed an increase of the impregnation yield that was accounted by the increase of CO2 sorption and increase of polymer swelling. So increasing the condition, it favors the impregnation of PLLA. Regarding aspirin and carvon, we didn't notice any change in the impregnation yield for them with the operating conditions. Aspirin have a very strong interaction with PLLA, so when it enter in contact with PLLA, it won't diffuse inside the polymer. Whereas carvon, in the case of carvon, its solubility into CO2 is very high. So the CO2 drug interaction is stronger than polymer drug interaction, which does not favor its impregnation. So after that, we focus on double impregnation. At 60 degrees C and 90 bar, we did not observe any specific phenomena. So the result is simply the sum of the impregnation of each drug. And at 80 degrees C and 30 megapascal, we observe that for ketoprofen and carvon, which is the blue and green bars, we observe a higher impregnation yield of ketoprofen than expected, which means we have a synergy between ketoprofen and carvon. And in the case of carvon and aspirin, which is the red and blue bars, we have a higher impregnation yield of aspirin than expected. So we have a synergy for aspirin. So how do we how do we explain it? So we had a look to the thermal properties of this polymer, and we observed that at both conditions, we observed a shift of the thermal characteristic temperature of PLLA. So a shift of the TG, shift of the crystallization temperature and of the melting temperature. And particularly, we noticed a shift of this melting temperature, but we also observed that after impregnation, the sample remained with the same shape, which means that in situ, we have the compounds that are being impregnated that provoke a partial melting and recrystallization of PLLA. During the melting of these crystals, it increases CO2 sorption. Increasing the CO2 sorption, more molecules can be impregnated. It increases this phenomena, so it is a cyclic phenomena up to reach the equilibrium. So for ketoprophene and carbon, both carbon and ketoprophene, if we have a specific look to DSC of PLLA impregnated with this compound, we observe that both of them plasticize PLLA. So both of them help their impregnation, which explains the higher impregnation of ketoprophene in that case. And for ketoprophene and aspirin, ketoprophene plasticize PLLA, and it will help aspirins that have some difficulty to diffuse in PLLA. So ketoprophene will help PLLA to be impregnated with aspirin. So now let's talk about the impregnation of an extract in one polymer. So this is a master degree of Amanda Jordan. We focused on the clove bud extract because it has a quite simple composition with only 4 majority compounds, and it has a large spectrum of bioactivity. And we first started by determining the composition of the crude clove extract by GC. It is mainly composed of eugenol, but eugenyl acetate also, beta-caryophyllene, and alpha-humulene. And we impregnated it into PLLA and polycarbonate. So for the impregnation, we work with the design of experiments, so I won't present it, I will go very fast. And we've noted that both pressure and temperature has an influence, and here I present the result for the impregnation of polycarbonate. So according to pressure, as you can see, we work at 10, 20, and 30 megapascal, and we observe that increasing the pressure, we have the drug loading that decrease. Why? Because increasing the pressure, we increase the extract solubility in supercritical CO2, and this very high affinity for CO2 is deleterious for the impregnation in the polymer. Whereas increasing the temperature, we observe different phenomena at 10 and 20 megapascal. With the increase of temperature, we observed an increase of the impregnation because we have an increase of the polycarbonate chain mobility, which increases CO2 sorption, which increases the impregnation. Whereas at 30 megapascal, we observe quite similar impregnation independently of the temperature. Then, using this design of experiment, we identified which are the conditions that permit to achieve a high impregnation yield. And it was noted that high temperature and low pressure were more favorable. So we select 2 sets of conditions, 60 degrees C and 10 megapascal, and 47 degrees C and 10 megapascal, in order to identify the composition of the extract in that 2 cases. And so to do so, after performing the impregnation, we extracted all the extract impregnated, and we characterized it by gas chromatography. And we've noted that comparing to the crude clove extract, we have quite a change of the composition of the extract. So first of all, we have no molecule of humulene impregnated. We have an increase of the proportion of eugenol in the extract and a decrease of eugenyl acetate and caryophyllene. And doing the same protocol for PLLA, we reach the same conclusion. So we explain it, and we need to go deeper in the explanation because these results are quite recent. But we expect to focus on the physicochemical interaction between each of these compounds and each of these polymers, and also to understand if one compound is more susceptible to plasticize more the polymer, and to explain this higher or lower impregnation yield in each case. But the result that we found is that the composition of the impregnated extract is not the same as the crude extract. And so the next step will also be to check the bioactivity. Does the bioactivity of the impregnated polymer is similar as the crude extract? So we are currently working on it. And finally, talking about CO2 source polymer, as I said, CO2 can be used as a reagent to produce polymer. And talking about polycarbonate, that is one of the polymers that we chose. Polycarbonate is conventionally synthesized by a polycondensation reaction of phosgene and bisphenol A. And phosgene is an asphyxiating has asphyxiating properties and is extremely toxic. And in this synthesis, the solvent used is methylene chloride, which is carcinogenic, and its recovery from wet water is quite difficult. So 8 years ago, the Japanese company Asahi Kasei proposed non-phosgene polycarbonate. So as you can see in this reaction pathway, we use ethylene oxide and CO2, and we end up with polycarbonate. So in that case, we get rid of phosgene and of methylene chloride. So we are working in partnership with Professor Christine Jérôme from the Center of Education and Research on Macromolecule in Belgium, and they are synthesizing polycarbonate by organocatalyzed addition. So this first reagent, which is the bis alpha alkylidine cyclic carbonate, is obtained from CO2. Then it is reacted with a diol in order to obtain this polycarbonate. And varying the diols that is used in this reaction, we can end up with a library of polycarbonate with different structure. And having different structure, we will have different physicochemical properties, different behavior in CO2, and different interaction with each of the 4 compounds of the Clove extract. And after that, we aim at blending it with PLLA in order to obtain blends with different morphologies that can influence the impregnation of each of these 4 compounds of the Clove extract, and in order to control better their impregnation. So we are currently working on it. I won't show any results from now because we are still trying to understand this complex synthesis and the different thermal properties, particularly that we have from these different polycarbonates that we synthesized. But as a conclusion of this presentation, so CO2 valorization here is used in this project at 3 levels. So for extraction of natural compounds from vegetal matrices, it is used as a solvent to carry this natural extract in the polymer, but it is also used as a reagent for polymer synthesis. Impregnation process of natural extracts involves specific physicochemical interactions, and the composition of the impregnating extract is different from the crude extract. And so the next step, as I said, is the bioactivity impacted, and how we will be able to use also the different polycarbonates that we are synthesizing to control better the impregnation of the different molecules from our extracts. So I would like to thank all my collaborators and also my students, FAPES with a financial agency from the São Paulo state. And thank you for your attention. Here you can find my email address, you can find my Google site, so if you are interested to see the different research that we are developing in my research group. And we are recruiting master and PhD students and open for collaboration. So I will be very happy if, to talk about the possibilities of collaboration. Thank you very much.
Thank you so much, Mathilde, for this very interesting presentation. So you can type questions in the chat if you have. We have one question from Vera Pandian already. Thanks for a nice presentation. When you use CO2 in supercritical conditions, have you ever noticed any reaction between the CO2 with polymers or with the extract during the impregnation process?
Thank you very much for this question. We haven't noticed any reaction because CO2 is carbon which is oxidized. And so it is a very stable molecule. So, for example, CO2 is used to produce other kinds of molecules and to be used in the energy fields and so on. And for this purpose, we need to use a very performant catalyst to change CO2 and make it react with other compounds to form the desired product. So CO2 is not a molecule that will readily react either with the polymer, neither with the molecules that we might impregnate in.
Thank you for your answer. We have another question from Avinash. Supercritical CO2 manufacture is also an energy-intensive process. Is it cost-effective when compared to traditional solvents?
So this is a very good question, and it's a very common question also. In fact, it depends on what you can achieve using traditional solvents. Using traditional solvents for performing this impregnation, for example, is not effective because you cannot reach such high drug loading or impregnation yield, as I said. And second point is that a study has been performed some years ago to compare the energy cost of a traditional impregnation process using traditional solvents and an impregnation process. And it has been shown that particularly it was for the textile field, that it was less it was more interesting to use supercritical technology than using a traditional impregnation process, because when we are talking about development of a product, we should not only focus on the step that is interesting for us, but also the post-treatments. And when we use organic solvent, we need to remove these solvents without changing so much the properties of the product that we have just developed. And this is energy consuming also and time consuming, because if you have a look to the application that I've shown, it is for food engineering and cosmetics and to develop implants, so for health products. And in these three cases, you need to respect very strict rules, very strict requirements. And to reach this low concentration of solvents, you need to have performance system to remove the solvent from the polymers, and this is cost effective. So these studies that have been published some years ago shown that, in fact, it was less energy consuming to use supercritical technology than using a traditional impregnation process. But of course, it should not be generalized, because depending on the solvents that you use, also the requirement from the FDA and so on change a little bit. So the concentrations that can remain in your product change a little bit. So you should make a comparative study of the different process based on the specificity of your system. And also the second thing that I would like to say is that the idea of integrating the extraction and impregnation process that we aim to target in some few years, I hope, is also in that way to use the same technology, so supercritical technology, but to decrease the energy consumption by using in two steps CO2 that is in its supercritical state. So normally we expect to decrease the energy consumption doing so.
Thank you. Very complete answer to this question. We have another question, so also from Avinash. Do you only work on polycarbonate or any other polyester or other polymers?
So I think that what he wanted to ask if we synthesize other polymers and polycarbonate using CO2. If this is a question, polyurethanes are currently also synthesized using CO2. So basically, polyurethanes and polycarbonates are the two classes of polymers that are more studied and that have their synthesis more controlled right now. But the possibility of developing new polymers using CO2 will depend a lot on the catalyses that are used in order to produce specific reaction to produce your monomer. So it should be expected that in the future, the spectra of polymers, the diversities of polymers that can be synthesized from CO2 will increase. But from now, I know that polycarbonates and polyurethanes are the two class of polymers that are the more studied and more known for this approach.
Okay. Thank you so much. Thank you again for the presentation and for taking the time to reply to the questions. Thank you to all the participants who joined us today, and I hope you enjoyed the webinar, and I hope you will come back to see one of the future webinars. So have a very good day, everyone, and take care.
Thank you.
Bye.
Bye.